Okay, so this is chapter 2. What I'm going to do with chapter 2 is I'm going to break it into 3 separate parts with the PowerPoint video. I'm going to break it up into 2.1 and 2.2, and then I'm going to do 2.3 through 2.5, and then I'll do 2.6 and 2.7. Okay, so sorry, just so you're aware, that's what's going to be happening. This is going to be pretty self-explanatory to those of you who already took chemistry, but I'm just going to go through it. If you have questions, you can let me know. So matter is anything that has mass and takes up space. We know that elements are basic building blocks of matter. They can't be broken down by chemical means. Now, when we're talking about human biology, there are 4 elements that we talk about most of the time: carbon, nitrogen, oxygen, and hydrogen. That is because those are the organic molecules. Carbon technically is the organic, but the other 3 are in there. Those are the 4 elements that make up 90% of the human body. Are there other elements? Sure. There's magnesium, there's calcium, there are a lot of other ones in there, but 90% of the human body is nitrogen, oxygen, and it's carbon, nitrogen, oxygen, and hydrogen. That's the basis for organic chemistry. It's also the basis for biochemistry. Those are the ones we're going to talk about more often than not because they make up 90% of the body. This is a periodic table. You know that the periodic table has 3 parts to it. Generally, you have the top is the atomic number. The atomic number tells you the number of protons and the number of electrons in a neutral atom, as they're shown on the periodic table. Then you have the element itself, and then below that you have the average atomic mass. And the average atomic mass is the average of all known isotopes, okay? Which means it's the mass of that isotope times its percent found in nature added together, okay? You will see mass number, atomic mass, and average atomic mass used interchangeably all the time. They're not the same thing technically. Average atomic mass is the average of all known isotopes. That's a decimal. Mass number and atomic mass should be the number of protons plus the number of neutrons. You see average atomic mass and atomic mass used interchangeably all the time. You also see atomic mass and mass number used interchangeably all the time. Just be aware that that happens. An atom is the smallest unit of an element that retains the physical and chemical properties of that element. Atoms bond together to form molecules. Now, technically, molecules are atoms that are joined together. They don't have to be different atoms. There are diatomic molecules, BROH, CLI, and F. Broncliffe, you'll hear me talk about them all the time. BR2, O2, H2, N2, Cl2, I2, and F2. Those are the molecules that are found naturally in their diatomic state, which means there's 2 of them stuck together. Compounds are a different story. Compounds have to be different different atoms. Different elements, yeah. Atoms of different elements. Sorry, I said that wrong. They're atoms of different elements. So molecules technically are just atoms bonded together. They can be the same or they can be different. Compounds should be different. You also see those 2 interchangeably used all the time anyway. Neutrons are neutral. They're uncharged. They're found in the nucleus. Protons are positive charged. They are found in the nucleus. Protons and neutrons are roughly the same size. They have about the same AMU. That's atomic mass unit. Electrons are teeny. They're found outside the nucleus. Quantum mechanical theory states that they're in an electron cloud, and you're looking really at a probability of finding an electron, not necessarily the actually finding an electron. It's a whole other science. But they call them electron shells. They're areas where you're probably going to find an electron orbiting around the nucleus. So electrons tend to be about 1/1860, the size of a proton and a neutron. So we say they have an AMU of 0. This gives you what I just said. This shows you the Bohr models where you have the protons and the neutrons in the nucleus and the electrons around the outside. Atomic number is the number of protons. It differs for every element. You change the number of protons, you change the element. You change the number of electrons, you have an ion. You change the number of neutrons, you have an isotope, okay? But atomic number is the number of protons. If that changes, you change the element, okay? the atomic mass is the average AMU for all isotopes of that atom, and here it is. This should say average atomic mass, and they use atomic mass. So you'll see atomic mass and mass number used interchangeably too. Mass number technically is the sum of the number of protons and neutrons together, because protons and neutrons are the only thing that provide any mass, so we just add them up. The atomic mass is the average of all known isotopes. It's technically the average atomic mass. Isotopes, as I said, same element, different number of neutrons. Radioisotopes are unstable. They emit an energy called radiation. Radiation can be used in many different ways medically. You can read about that in the book. It's imaging the body, killing bacteria, sterilizing equipment, killing cancer, but it can also damage cells. And I want you to read that section for sure in the book. These are the couple of medical uses. This is looking at the thyroid. This is looking at the brain. Looking at the thyroid, what they do is they put you on a low iodine diet for a couple days, and then they inject you with radioactive iodine, and then they take an image so that they can see how much iodine your thyroid is picking up. If it picks up too much, it's too fast. Too slow, or too little, it's too slow. Molecules and compounds, I just talked about this. Molecules are just atoms bonded together. They can be the same thing. Compounds are made of different atoms, like H2O. And the two types of bonds that join them are ionic or covalent. Ionic means that they are transferring electrons. The electrons are going back and forth between them. One becomes positive, one becomes negative. If you lose electrons, you become positive. If you gain electrons, you become negative. So you have a negative and a positive. They stick together. That's electrostatic attraction, is an ionic bond. Covalent bonds are sharing of electrons. The atoms come together and they kind of share those electrons in their outermost shell. That's a covalent bond. Covalent bonds tend to be a lot less strong than ionic bonds are. Ionic bonds have to do with the valence shell. Again, if you already took chemistry, you should know this. Looking at a periodic table, you take out the transition elements. Starting on the left side with the hydrogen, it's 1, 2, skip transition, 3, 4, 5, 6, 7, 8, with 8 being the noble gases. 8 is where everybody wants to get. So, and it ends up as 8 or 0 with some of the first elements, but that's, what they want is that full outer shell. Okay. This is the formation of an ionic bond. Sodium transfers an electron to calcium. Sodium becomes negative, not calcium, chlorine, sorry. Sodium transfers an electron to chlorine. Sodium becomes positive, chlorine becomes negative. Positive and negative, electrostatic attraction, they come together. Covalent bonds, they're sharing. Like I said, you can have double, triple, and quadruple covalent bonds. Carbon is the only one that can really do a quadruple. Sometimes sulfur is weird. It can do an octet. It's a little expanded octet, so it's a little different. But oxygen will do a double bond. Nitrogen will do a triple bond. Carbon will do a single, double, triple, and quadruple. Carbon can only do a quadruple bond with itself. But that means that they're sharing more than one electron. So a single bond is a share of 1 electron. A double bond is a sharing of 2. A triple bond is a sharing of 3, like that. Here's an example of a covalent bond. You can see that these 2 hydrogens are sharing their electrons with oxygen. Here you can see this ends up being a double bond because each of these oxygens are sharing 2 electrons with each other. So you end up with that double bond in there. Okay, that's check your progress. Okay, water. Water has specific properties. First of all, it's a polar molecule. What does that mean? It means that water has a partial negative side and a partial positive side. Oxygen and hydrogen have completely different electronegativities. Oxygen's is much higher than hydrogen. Oxygen's electronegativity is high, which means it has a greater pull on the electrons. So since the electrons are closer to the oxygen gets a partially negative charge. More electrons, more negative. The hydrogen doesn't have as much pull, so they're not as close to the hydrogen, gives it a partial positive charge. So what you end up with is a molecule with a partially negative end and a partially positive end. That's a polar molecule. Okay. What happens here is that how they depict this is by these little things right here. They're technically sigmas, like what we used with standard deviation. but they have like that little curly Q thing at the top of them there. So you can see that they use a little curly Q thing with the negative and the positive on this end. So this shows that this is the positive end and this is the negative end. A hydrogen bond is an attraction between a slightly positive hydrogen and a slightly negative oxygen or nitrogen on another molecule. So what happens is, I'll show you on the next slide, you have the partially positive end here being attracted to this partially negative end here. You have the partially positive end here being attracted to this partially negative end here. You have this partially negative end being attracted to the partially positive, and they're depicted by these dotted lines. They're not super strong, but they're strong enough. They're not as strong as an ionic bond. They're not as strong as a covalent bond, but they are strong enough to produce things like surface tension and adhesion and cohesion. So they are strong enough that you have to break through the surface of water, okay? And they're strong enough that it allows water to have that top on it where like little, like little water spiders can walk. And if you happen to jump off of a bridge, you got to break through that surface tension, or it's the same impact as hitting concrete. So they're not super strong like this says, like it said back here on that last slide. I can't go back to it now because I'm recording, but it did say that they're relatively weak. They are, but they're still pretty strong. They're not, they're not ionic, they're not covalent, but they're still strong enough to provide properties, water properties that we wouldn't necessarily have if they didn't have them. The reason that we have all these properties of water, and you need to know these properties of water, they're in the book, is because of hydrogen bonds. So water is liquid at room temperature. It has a high heat capacity, which means it takes more calories to raise 1 gram of water 1 degree Celsius than other liquids. There's a high heat of vaporization. Those hydrogen bonds have to break in order for that water to boil, and it's also why sweating cools us off. If you look here, you can see it takes 540 calories to go from a liquid to a gas. It only takes 80 to go from a solid to a liquid. Okay, so the heat of vaporization in water is pretty high. Water is also a solvent. A solution is water with dissolved solutes. Most salts dissociate in water, which means they are compounds, they're ionic compounds. They break apart into their respective ions. So if you have NaCl, the Na breaks apart, the Cl breaks apart, and the water surrounds it. Okay, that is an important property because it allows things to dissolve in water, and it allows a lot of our body processes to work. Water is a solvent. So anyway, so water we said was a polar molecule. Polar dissolves polar. Okay, so polar molecules, other polar molecules that have a separation of charge, are called hydrophilic, meaning they're water loving. Hydrophobic molecules don't. That's nonpolar. Nonpolar are things like oil. Okay, in nonpolar covalent bonds, the electrons are shared equally, so there's no partial charge. So again, oil. Cohesion and adhesion. Cohesion means that the water molecules cling to each other. That's what causes surface tension. Adhesion means that they cling to other things. Capillary action is a good one of these. Okay. Frozen water is less dense than liquid water. The reason for that is because of this lattice structure. Most molecules do not have this, or most compounds or molecules even, do not have this lattice structure. The lattice structure of water allows the solid form of water to be less dense than the liquid form, and that is very important in living things because the colder the water gets, the more it floats. That's a good thing. When we have a pond, we want water, we want the ice to float, act as an insulator so that things inside can still live. If you don't want the water to freeze from the bottom up, everything would die. So frozen water is less dense than liquid water. That's another one. That brings us to acids and bases. Acids and bases. Acids are substances that dissociate in water and they release hydrogen ions. Hydrochloric acid is a strong acid. It will dissociate into H pluses and Cl minuses. The higher your H plus content, the more acidic you are. Bases take up hydrogen or they release hydroxide. Okay. Sodium hydroxide, NaOH is a strong base. This down here just shows you the formation of heavy water, which is water when it takes up an extra H plus and it becomes H3O. The pH scale goes from 0 to 14. 7 is about neutral. Below 7 is considered acidic. Above 7 is considered basic. Acidic is 0, like I said, 0 to like 6.8-ish. Alkalinity is the same as basicness, okay? So bases are more alkaline. This is the pH scale. We'll talk a little bit more about this in class, just to make sure you understand. You'll notice that the acidic, the H plus ion concentration is a lot lower down here than it is up here. If you're a base, you have a higher OH concentration, a lower H plus concentration, but the pH scale literally just measures the hydrogen ions, the H pluses. So lower down here is acidic, higher up here is basic. As you move, you go from a pH of 2 to a pH of 3, you increase your H plus ions by a factor of 10. A buffer is a solution that resists changes in pH when acids are added or bases are added to it. Very important within the body because you got to keep that pH steady. pH in the body should be somewhere between 6.8 and 7.8. Generally, they say blood is about 7.8. That really depends on your body chemistry. Your blood can go, you'll see it a lot of different places. It prevents changes in pH. I'll go through the carbonic acid buffer system with you at length in class, so don't worry too much about this right now. And I'm going to end that here.